All right, so looking again at this replication of DNA, again, these two strands have to unwind. We refer to this area where it separates as the replication fork. And in this open area is where DNA polymerase is going to come in and bring in the new nucleotides to pair up and create these new strands on either side of the DNA. Okay? So again, DNA polymerase brings these strands together. DNA helicase is the one that separates them. Okay, and so we can see these new strands are forming on both of these old strands. Okay, so each strand has a new one attached to it. So this is referred to as semi-conservative replication, because when we get these two new double-stranded DNAs at the end, each one is half from the original strand, half new. Okay? And so this is the conservative model where the old strand completely stays old and we get brand new strands through this process. Semi-conservative, each one is half new, half old. Dispersive, it's random. And so we see that the semi-conservative model is the one that fits best with what we observe within DNA replication. Okay? Now, when we look at how DNA replicates itself and we look at the way DNA polymerase can act, it can only move in one direction, 3' to 5'. Okay, so we look at this strand of DNA, and this is based on the positions of the carbons and the sugars, which isn't a big deal for you to know, but just know that one end is 3' to 5', and the other side of the DNA runs in the opposite direction. So DNA polymerase can run this direction up on the 3' to 5' or down on this end over here. Now the issue is the replication fork doesn't move in this opposite direction. So DNA grows in opposite directions, but it has some things that it has to take care of as it's doing this opposite direction strand. Okay, so when we look at this strand, here we've got our DNA helicase creating this replication fork. It's breaking the hydrogen bonds and opening it up. So this is 3' to 5' here. And so the DNA polymerase can just continue going. And as that DNA helicase continues down this strand of DNA, the polymerase here, working 3' to 5', can continue on following it, and we have no problem. Now, with this other strand, it still has to go 3' to 5'. So as you can tell, it's doing this in pieces. So it started off here, go 3' to 5'. The DNA helicase continued moving down. That DNA polymerase detaches, reattaches, makes its way 3' to 5'. All the while, DNA helicase is continuing to make its way down. It detaches, reattaches, and so on. And so this DNA polymerase on what we call the lagging strand is going to have to continuously detach, reattach to do the replication on that lagging strand. Okay, that one that goes 5 to 3' in the opposite direction. Okay. So because we put these together in pieces, we then need an enzyme to come in and put them back together. This enzyme is ligase. Ligase is going to come in and glue together these Okazaki fragments, these pieces that are put together by this DNA polymerase that's working on that lagging strand. Okay, your DNA from each of your cells, if you were to take that DNA out from one cell, stretch it out 2 meters long, that's a lot of DNA. Okay, so what we end up with at the end of DNA is we get two double-stranded DNA molecules identical to one another. Okay, they should be perfect copies so that each cell gets exactly what you need. All of this replication is going to be happening in the nucleus of the cell. Okay. Errors, do they occur during DNA replication? Absolutely. We replicate at 700 nucleotides per second, which seems fast, but we've got 3 billion nucleotides to copy, so it still takes quite a while. 1 in every 10,000 base pairs, there's a mistake. Okay, so it's pretty dang good at what it does, but it's not perfect. DNA polymerase can go back and fix a lot of these, but we still get a mutation in every 1 million to 100 million or so uh, replicated nucleotides. Okay, a mistake or error in our DNA is a mutation. Okay, you want to know that term. Okay, mistake in our DNA is known as a mutation. Eukaryotic cells are pretty good at repairing. They don't tend to get quite as many mutations as prokaryotic cells. These cells that do not have a nucleus, they replicate much faster. And so if we look in this test tube, 10 bacteria in each millimeter from this tube would have a mutation based on this replication and the inability to go back and fix these things, which is why things like bacteria are able to mutate so quickly. Oftentimes, those mutations don't do anything. Sometimes they're bad, but every once in a while, there's going to be a beneficial mutation. And if there are so many of them, they can sometimes gain resistance to antibiotics or whatever it might be. Okay. So again, mutations, they can be natural, just issues with DNA replication that happen. Various chemicals can cause mutations. Radiation like UV light that from the sun, right? That's why you put on sunscreen. Things like X-rays can also cause mutations. Okay. And this specifically talks about a thymine dimer. It's a specific type of mutation caused by ultraviolet radiation. Okay, and these happen pretty commonly, but most of the time our body's able to go in and fix them before they cause any issues. Okay, again, how much DNA is there in a human cell? Our DNA strands have 3 billion base pairs. That's a lot of bases to copy, but our cells are constantly doing it. So when we compare our DNA to other organisms, okay, we've got 3,400,000,000 base pairs. So, that's pretty complex. But onions have 18 billion. Salamanders have 84 billion. Amoebas have 670 billion base pairs. So when we're really looking at complexity, it really depends on how you define it, okay? Because these organisms have more DNA base pairs than we do. Okay, maybe our DNA is just more efficient doing what it needs. I don't know. Okay, but there's a lot to look at here. And that is the end of part 1 for DNA.